Hi, I'm Mark Cerny. Today I'd like to do a deep dive into the technology behind our latest console, PlayStation 5 Pro. Now, to be clear, this is a bits and bytes talk with no game footage at all. Principally, I'll be explaining what we put into the PlayStation 5 Pro GPU and why. Historically, every 7 or so years, there's enough interesting technological advances that we release a new generation of console, like PS3 or PS4 or 5. These introduce broad improvements like a more powerful CPU and GPU, and also significant new capabilities like compute shaders on PS4 or the SSD and 3D audio on PS5. Games can then be created with the whole console feature set in mind. It allows for a tremendous step up in what the player experiences. It does take a certain amount of time for game creators to get up to speed with that new console. But we're all prepared for that because the benefits of moving to that new generation are so high. Recently, there have also been console releases during a generation, like PS4 Pro and now PS5 Pro. These are much more tightly focused, typically on the GPU. And what developers are making are improved versions of games, never dedicated games, so targets for Pro consoles are very different. First, the work that needs to be done by the game creators for the Pro console needs to be kept to an absolute minimum. They already have a lot of pieces of hardware they're supporting. We don't want to add much to that burden. And second, those tightly focused improvements need to be pretty significant. The games have to play noticeably better. One of the trickier aspects of console design is that creating a console is roughly a 4-year journey. In order to launch PS5 Pro in 2024, we were actually trying to work out the key feature set in 2020. In other words, at a time before PlayStation 5 had even been released. And of course, what we came up with was the set of improvements we've been calling the Big Three. First, there's that larger GPU. The idea is simple. Pretty much anything the game is rendering on PlayStation 5 should get a lot faster on PS5 Pro. Second, there are the upgrades to the ray tracing hardware. Those games that move to the new architecture should get a substantial additional speed boost. And finally, there's AI-driven upscaling. The upscaling technology is a combination of custom hardware for machine learning and an AI library called PlayStation Spectral Super Resolution, PSSR for short, that runs on top of that hardware. PSSR analyzes the game images as it upscales them and can add quite a bit of crispness and detail. Now, to do all that, we needed a larger and more capable GPU. This is what we used on the original PS5. It's a GPU from our partner AMD. More specifically, it's an RDNA 2 GPU, meaning that it used the second generation of AMD's RDNA 2 technology. The GPU has subunits called workgroup processors, or WGPs. PlayStation 5 has 18 of them. The GPU on PS5 Pro is much larger. It has 30 workgroup processors. It's also what I'm calling a hybrid RDNA GPU, which is to say, it combines multiple generations of RDNA technology. The base technology for PS5 Pro is somewhere between RDNA 2 and RDNA 3. I'm calling it RDNA 2.x. As I'll shortly explain, that choice makes it much easier for game developers to port their games to the new console. Ray tracing uses what I'm calling future RDNA technology. It's roadmap RDNA that's well past the feature set today. It's showing up here first. And machine learning is custom, or to be more specific, it's custom enhancements to RDNA. And just to be clear, I may say machine learning or ML or AI today. These are just different words for the same topics. Now, to support that GPU and the overall plan for PS5 Pro, we needed faster memory and we needed more memory. The faster part is pretty simple. The system memory on PS5 Pro has a bandwidth of 576 gigabytes per second, which is 28% higher than PlayStation 5. More memory is needed for a variety of usage scenarios on PS5 Pro. Integrating PSSR takes memory. A few hundred megabytes are needed for its internal buffers. Adding ray tracing takes memory. Ray tracing uses data in the form of an acceleration structure that can easily be a few hundred megabytes in size. And if the game is targeting higher resolution, that can take memory as well. That can be just a little memory, perhaps if the maximum rendering resolution is being increased a bit, or it can be a lot of memory, for example, if the game is targeting 8K. So we supply over a gigabyte of extra memory to the games, and we do this in the same way we did on PS4 Pro. Which is to say, we added a hidden slower RAM. We used DDR5 for that, and moved a lot of the operating system into it. That keeps games, which need high bandwidth, in fast memory. Getting back to the hybrid GPU, I'd like to take you through each of the three aspects of our strategy, beginning with the choice of RDNA 2.x as the base technology. AMD is continuously updating the GPU technology. RDNA 3 has more functionality and is more performant than RDNA 2. There's even a chance to bring in future RDNA technologies like we did with ray tracing. If we're making a new generation of console, of course we want the latest and greatest, but with a mid-generation release like PS5 Pro, we also have to consider that a single game package needs to support both PS5 and PS5 Pro. That limited the degree to which we could adopt RDNA 3 technologies. For example, games have something called shader programs that execute on the GPU. A game might have over 100,000 of them. If we adopted RDNA 3 technologies to the extent that code compiled to run on PS5 Pro wouldn't run on PS5, that would mean creating two versions of each executable piece of code. One for PS5, another for PS5 Pro. That's a massive complication. The game package needs to be patched to include that second version, and then the game needs to either selectively load just the appropriate version, or find room for both versions in system memory. It's a big burden for the developers. Consequently, PS5 Pro uses a version of RDNA that I'm calling RDNA 2.x, which is bringing in a number of features from RDNA 3, but not anything that would cause that degree of complications. For example, aspects of vertex and primitive processing are faster on PS5 Pro. That's from bringing in parts of the geometry pipe from RDNA 3 that are powerful, but either trivial for the game to adopt, or better yet, invisible to the game program. One thing I'd like to clear up is the erroneous 33.5 teraflop number that's been circulating for PS5 Pro. That number isn't anywhere in our developer docs. It comes from a misunderstanding by someone commenting on leaked PS5 Pro technical information. Part of the confusion comes from RDNA 3 architectures having double the flops of RDNA 2 architectures. Now, to quote Digital Foundry on this topic, it's a nice little bonus to have twice the flops, but it doesn't do anything like double real-world performance. So there's a certain amount of flopflation going on here. We did not bring in the doubled floating point math from RDNA 3 because achieving that bonus in performance would require a recompile for PS5 Pro. And as I said, having two versions of each compiled piece of code would create more work than we're comfortable asking the developers to do. Here, then, are the correct stats for PS5 Pro. It's pretty simple. PS5 Pro has 30 workgroup processors, which is 67% more than PS5 has, so the flops should be 67% higher as well. If we assume a pretty common operating frequency of 2.17 gigahertz, the math works out to 16.7 teraflops on PS5 Pro. Of course, teraflop numbers are pretty meaningless. What isn't meaningless is the performance of the PS5 Pro GPU. 67% more workgroup processors means that we can create synthetic tests that show 67% faster processing. In practice, though, there are a lot of factors involved, such as memory bandwidth or even how a particular game engine responds to the details of the new architecture. So a game team might be looking for something more like a 45% increase in rendering speed. That's still a huge improvement, though. At that performance, it means that if a game is running at 60 FPS and is taking 16 milliseconds to render on PS5, then that same frame could be rendered in 11 milliseconds on PS5 Pro. That leaves 5 milliseconds to do something new and exciting, like adding ray tracing, which is the second of our 3 key improvements on PS5 Pro. There's a passion in the game development community for ray tracing. Even in 2020, before the launch of PlayStation 5, we could see creators using ray tracing to add reflections and improved lighting to their games. At the same time, calculation costs for the rays were pretty high, so when we kicked off development of PS5 Pro later that year, one of our top priorities was finding ways to accelerate that computation. Those conversations with AMD led to our very nice feature set that's showing up here first. Note that there's two factors increasing the performance. It's not just that there are 67% more workgroup processors. Thanks to the new feature set, each one is more capable. It's difficult to quote an exact speedup because it's very dependent on specifics of usage, but we commonly see the calculation of the rays occurring at double or triple the speed of PlayStation 5. The most impactful new features in PS5 Pro relate to a new acceleration structure and stack management in hardware. There's a lot to unpack here. First, let's talk about the improvements related to the acceleration structure. In order to use ray tracing on PlayStation 5, you need to have data in system memory that describes your geometry, say 1,000,000 triangles worth. Then there's something called an intersection engine inside each of the workgroup processors that lets you check to see if a ray hit any of those 1,000,000 triangles and which it hit first. It would be too slow to test each ray individually against all 1,000,000 of those triangles, so there are also boxes in the data structure. These boxes let the ray tracing hardware more efficiently home in on the triangles that might be intersected. For example, we can see that the ray misses that upper left box, so there's no need to test the ray against any of the triangles contained within it. The boxes are actually in a hierarchy, starting with big ones and progressively reducing in size. Every time we hit a box, we test against the boxes nested within it until ultimately we reach some triangles we can test against. Together, those triangles and boxes are called the acceleration structure. On the original PlayStation 5, we used a type of acceleration structure called a BVH4. BVH stands for Bounding Volume Hierarchy, meaning hierarchy of boxes, and the 4 indicates that the boxes are in groups of up to 4. The intersection engine can then check a ray against up to 4 boxes a cycle or 1 triangle. Generally speaking, there's a lot more checking against boxes. That's what primarily determines the performance of the ray calculations. PS5 Pro adds a BVH8 option for the acceleration structure, where the boxes are efficiently encoded in groups of 8. And the intersection engine runs twice as fast. A ray can be tested against 8 boxes a cycle, or 2 triangles. That doubling of the ray intersection speed has a great theoretical impact on ray tracing performance. But real-world cases also need a solution to the problem of divergence. That's what led us to our second big feature, which is stack management in hardware. Before I can explain that feature, though, I have to explain divergence. The workgroup processors handle groups of 32 or 64 items at once. They could be pixels or vertices or rays. This strategy is called SIMD, Single Instruction Multiple Data. So SIMD32 means the same operations are being performed on 32 items. This works very well when all 32 items are getting the same treatment. For example, 32 pixels from a triangle are all reading from locations in the same texture, and then those 32 pixels all need a lighting calculation. This is called coherent processing. There's a difficulty that arises with divergent processing, where some of the pixels need one action taken and others need something else. In this case, it's quite possible that the processing takes twice as long. In the limit, if all 32 items need different handling, it's possible to be dozens of times slower. So when 32 rays are being processed together, the degree of divergence has a big impact on performance. Ray tracing can be fairly coherent. When we compute simple shadows from the sun, the rays are all parallel. But ray tracing can also get extremely divergent. If rays are bouncing off of a curved surface or a bumpy object, then potentially they're all heading in different directions. The shader code needed to handle divergent rays on PS5 is reasonably complicated. Part of what the code has to do is manage a stack. The internal structure of the BVH is quite complex, and each of the 32 rays can be traversing it in a different fashion. On PS5 Pro, stack management is in hardware, which greatly simplifies the shader program. It's shorter, which means it's faster, and since it's handling fewer cases, there's less divergence, which further increases the speed of execution. You may have noticed that there are now 2 versions of the code that are needed, a longer one for PlayStation 5 and a simplified one for PS5 Pro. But this need for 2 versions only applies to shader programs that are calculating how rays travel through the scene. There's typically not too many of those. In fact, with some games, it's just a single shader program that needs the 2 versions. Putting that all together, It's great to have the higher performance, but even better, we're seeing more consistently high performance on PS5 Pro. That consistency comes from the improved handling of divergence. Performance testing on PS5 Pro tends to show a good boost for the coherent cases like shadows or reflections off of flat surfaces. But a much nicer boost for the divergent cases. The stack management hardware is really helping there. Having more consistent performance across a broad set of use cases will go a long way towards easing adoption of ray tracing. The final improvements to the GPU are for machine learning. There are a lot of uses for machine learning or AI, whichever term you prefer. Large language models and generative AI are quite interesting tech, but with ML, it's also possible to go after a very specific target, which is to give the games a graphical boost. One of the key ways that can work is that the game renders less. There's 8 million pixels on a 4K TV. If the game renders sparsely, say a quarter of those pixels, it can do it a lot faster. And then the right neural network can intuit how to fill in those gaps and make a high-quality image. Another way to think about this, which is not quite as accurate, is that the game renders a smaller, lower-resolution image and then uses the neural network to upscale that image. This is called super resolution, and it's part of a whole family of strategies that reduce the work involved in rendering the game images. There's also frame generation or frame extrapolation, where a neural network inserts additional frames between the ones the game renders. That can really reduce the choppiness of low frame rate games. Neural networks can also be used to turn noisy, staticky images into smooth ones, which is an issue that crops up frequently, particularly with optimized ray tracing. Having said that, super resolution is definitely the focus of our current efforts. It's important to note that high-quality upscaling changes the way we should be thinking about game rendering resolution. Let's imagine 3 games that are rendering at various resolutions. A reductionist view on this is that the 1440p game engine is the best, and that the 1080p game is clearly flawed. But after a super resolution pass, these are all ending up at 4K resolution for display. The conversation really needs to be about what's important: image quality. When game creators improve their lighting or materials, or add ray tracing, then rendering each pixel can get more expensive, and the resolution will drop. They move up on this chart. And that's perfectly fine, as long as the upscaling technology is ensuring that the result is a crisp, beautiful image and not a blurry one. A different way to say that is that high-quality super resolution lets game creators focus on fewer, richer pixels and significantly improve the resulting image quality. It's a world where internal rendering resolution is not the primary concern. That's the world we want to be in. When we're using these strategies for graphics, the work isn't exclusively ML. The neural networks tend to be preceded by conventional processing and followed by some as well. It's the piece in the middle that's the neural network. More specifically, it's a type of neural network called a CNN, which stands for Convolutional Neural Network. Here's a simplified CNN for super resolution. It's not quite the one we use in PSSR, but close enough for the purposes of this conversation. You can see a lot of images. In the language of machine learning, they're called tensors, but basically they're images with many bytes of data per pixel. The colored arrows are the layers of the network. They are processing those images. There's quite a few of them as well. Let's zoom in on the first layer. Its input is a game image, 4K RGB. Perhaps it's a quickie upscale of what the game rendered. The first layer does lots of matrix math and then outputs another 4K image, now with substantially more information per pixel, maybe 16 bytes describing edges and the like that the neural network found in that input game image. The second layer then picks up the output of the first layer and does a lot more matrix math. The resulting image might reflect some deeper understanding about what the game rendered. There's also layers that reduce the size of the images. Downsizing to 540p or even 270p lets the neural network efficiently analyze larger scale structures in the input game image. As you can tell, there's a phenomenal amount of math going on here. Easily 10,000 operations are being performed on every input pixel. And we need to do that math in something like a millisecond. Consequently, ML hardware needs very high performance, typically hundreds of trillions of operations per second. Note that we don't call those teraflops because they're integer operations. Instead, we say TOPS. There were a number of early decisions we had to make. The very first was deciding where in the hardware we would put whatever would do all of that matrix math. Generally speaking, there's two options. One option is to put ML capabilities into a GPU. Of course, that's additional logic so the GPU gets larger. Or one can add an NPU, a neural processing unit. NPUs are brilliant at executing neural networks, but perhaps not so good with the pre-processing and post-processing surrounding the CNNs. The deciding factor was the order of graphics processing within a frame. With this approach, most rendering in a frame is done at low resolution, maybe 1080p. Then machine learning is used to upscale to 4K, and there's no more rendering that can happen until that upscale finishes. So we need to process that neural network as quickly as possible, which is to say, we need very powerful ML hardware. The more powerful, the better. That need for power is what pushed us towards using an enhanced GPU. The choice was either adding a large NPU or making more moderate enhancements to the GPU. The next big decision was where all of this technology was going to come from. When we were starting the PS5 Pro project in 2020, we knew that we would need performant ML hardware and a high-quality neural network for super resolution. But we're not looking for ML hardware that's generically high performance. We need something that's optimal for our specific kinds of workloads. And our typical workload is a lightweight CNN, something that can run in a millisecond or so and has a lot of little layers. Broadly speaking, you can license tech or purchase tech or build tech, but once you're licensing technology, that's what you're doing forever. So in 2020, despite the degree of effort required, we decided to build our own hardware and software technology. I'll start with the hardware. We made a set of targeted enhancements to the RDNA shader core and the surrounding memory systems. We're calling it custom RDNA, as it is custom hardware created to our design specifications, but within the overall RDNA architecture, and of course, implemented by the RDNA experts at AMD. Our target for the peak computational capabilities was 308-bit TOPS, which is to say, 300 trillion operations a second using bytes as input. There's a lot of thought that needs to go into the details of exactly how that math functions, but adding that amount of raw performance is not terribly hard to do. The difficulty is memory access. PS5 Pro has 576 gigabytes a second of bandwidth to system memory. When we compare that bandwidth with the computational capability of 300 TOPS, it's clear that it's easy to be bandwidth limited. Let me give two examples. If we do a computation where we read a byte as input and then eventually write a byte, that's 2 bytes on the bus. And the balance point of the system is about 1,000 operations on that byte. If we're doing more than that, we have a well-designed system. The 300 TOPS is being meaningfully utilized. If we do less than that, though, we are bandwidth bound, and we're wasting some of that machine learning capability. 1,000 operations is a lot. Alternatively, to understand this issue, we can take a look at one of the layers of the network, say the second layer from the example I showed before. Let's imagine we have to read that input image and that it has 16 bytes of information for every pixel. That's about 128 megabytes on the system bus. Then we do our math, say a pointwise convolution, and write the output image, which is another 128 megabytes on the system bus. We are completely bandwidth bound. We're only using something like 3% of our potential 300 TOPS. So we're throwing out 97% of our performance. And those reads and writes are going to take half a millisecond just for this one layer. That's almost half of our budget for the entire CNN. One strategy for getting around these bandwidth issues is to fuse layers. The idea is to read up that input image, process the first layer, and then stick the results somewhere, maybe in fast on-chip memory, where the second layer can quickly and easily get access to them. As a result, we're reading from system memory once and writing once, but now we're processing 2 layers of the CNN and using something like 6% of our 300 TOPS. Still terrible, but an improvement. What we really want here is a fully fused network. That's the holy grail of neural network implementation. With a fully fused network, you're reading the input game image from system memory at the very start, processing all of the layers of the CNN internally on chip, and then writing the results back to system memory at the very end. With bandwidth that low, that 300 TOPS number is finally meaningful. There's two problems we need to solve, though. The first relates to the amount of on-chip memory required. There's 8 million pixels in a 4K image. If each pixel needs 16 bytes, that's about 128 megabytes. In terms of on-chip memory, that's a lot. Luckily, we don't need to process the whole screen at once. We can subdivide the screen and take just a piece of it at a time through the neural network. Let's call that piece a tile. Problem solved, right? The difficulty we encounter is that as we are processing the tile, bad data creeps in from the edges, so we have to throw out part of our results. The smaller the tile is, the higher the proportion of data that has to be discarded. There are therefore effective limits to how small we can make the tile, and correspondingly, there's a certain amount of fast on-chip memory that's key if we are to achieve that goal of a fully fused network. The other problem we need to solve relates to the bandwidth of that on-chip memory. Our targets are incredibly high. We'd like many, many terabytes per second. When you think in those terms, everything seems small. For example, we could increase the size of the GPU's L2 cache and try to use that for the on-chip memory. But unfortunately, the L2 bandwidth is just a few terabytes a second. This memory problem was the starting point for our custom design. From there, it's been almost a 4-year journey. I'll hit a few high points of the hardware architecture, beginning with the memory we ended up using. It turns out we do have fast on-chip RAM in the RDNA architecture with an aggregate bandwidth of 200 terabytes per second. We just need to change our mindset. What we're doing on PS5 Pro is using the vector registers in the workgroup processors as that RAM. Each workgroup processor has 4 sets of registers, each 128K in size, and with a bandwidth of over a terabyte per second. 30 workgroup processors therefore give us 15 megabytes of memory at a combined bandwidth of 200 terabytes per second, which is to say several hundred times faster than system memory. Of course, the roadmap RDNA's architecture and instruction set required some modifications to take better advantage of that register RAM. We ended up adding 44 new shader instructions. Those instructions take that freer approach to register RAM access and also implement the math needed for the CNNs, which is primarily done in 8-bit precision. These instructions are specifically designed to operate in a takeover mode, where each WGP processes the CNN for a single screen tile. By the way, the 300 TOPS number has been a real mystery since it leaked early this year. No one on the outside has been able to derive that number from the workgroup processor count and the GPU frequency. The secret is that there are instructions that perform 3x3 convolutions. Those use 9 multiplies and 9 adds for a total of 18 operations. And at that pretty common GPU frequency of 2.17 gigahertz, the performance really does work out to 300 TOPS. Here's the math. The CNNs also need 16-bit math, so there's a number of instructions for that. These instructions tend to be a bit simpler and more straightforward. We kept the chip area and the cost low for the 16-bit math simply by targeting lower 16-bit performance, because most of the processing in these CNNs can be done with 8-bit operations. As for 32-bit math, nothing in the CNNs particularly seems to need it, so we just left it as is. Our custom RDNA solution also involved a number of additional features, which I'm going to skip over so I can get to the other half of what we built, which is the neural network for super resolution that we created to run on top of that custom RDNA architecture. PSSR is an original PlayStation design. The full name, of course, is PlayStation Spectral Super Resolution, and that spectral is branding. It doesn't refer to any particular aspect of the algorithm. Just like we have Tempest for audio tech, we're using Spectral for our ML libraries for graphics. One of the project goals for PSSR is ease of adoption, so it uses essentially the same set of inputs as FSR or DLSS or XeSS. Those strategies use the pixel color of the current frame, but also depth information and motion vectors that give the flow of the pixels between the previous frame and the current frame. PSSR is not quite a drop-in replacement for the other strategies, but it's close. Having said that, PSSR is designed for consoles, so its primary use case is a little different from the others. PC games tend to render at a fixed resolution and with frame rate that varies based on scene complexity. Gaming monitors can handle that variable frame rate. So a typical PC game scenario is render at fixed resolution, upscale by a fixed 2:1 ratio, display at fixed resolution. In contrast, console games tend to have a frame rate that's fixed because they're displaying on a 60 FPS TV. What varies is the rendering resolution. If the scene is complex, then the rendering resolution is lower. If the scene is simpler, the rendering resolution is higher. Since the display resolution is usually fixed at 4K, PSSR needs to handle a continuously changing upscaling ratio. That scenario is primarily what we design for and train for. Of course, PC games are increasingly supporting variable rendering resolution, and all of these upscaling strategies can handle fixed upscaling ratios and variable upscaling ratios. I'm just pointing out that the focus with the PSSR project has been a little bit different. So with those goals in mind, starting in 2021, we considered a lot of types of neural networks. They were all recurrent networks, which is to say, they feed some of the results back in as input. For what it's worth, we looked at flat networks that just run at the display resolution, networks that run at the lower rendering resolution with a final bump up to display resolution, autoencoders that step down the resolution and step it back up, and UNets that do the same, but with different connectivity. And that's where we ended up. PSSR is a recurrent UNet. We also learned just how much work remains after a network is chosen. We did a lot of training and then did beta releases to select developers and got to see all kinds of issues cropping up once PSSR was actually integrated into games. And that required yet more training passes. Some of those issues were trivial. We found out that one game used a perfect blue in its sky, and PSSR had never seen perfect blue in its training. It had no idea what to do with it. Of course, some of the issues we encountered were much more complex. Looking back at the 4 years since we started this project, I'm so glad that we made the time-intensive decision to build our own technology. Results are good, and just as importantly, we've learned so much about how AI can improve game graphics. It can only make our future brighter. So that was the background and details of our improvements in these 3 key areas on PS5 Pro: the larger GPU, the advanced ray tracing, and the AI-driven upscaling. I'm going to restate those 3 somewhat, and then I'd like to take a moment to do something we very rarely do, which is talk about the future. Specifically, I'd like to talk about the future potential in each of these 3 key areas. First, there's rasterized rendering, by which I mean the conventional rendering strategies that were all we had up through PS4 Pro or so. There's not a whole lot of growth left here. It mostly has to come from making the GPU bigger or memory faster. Ray tracing is different. It's still early days for the technology, and I suspect we're in for several quantum leaps in performance over the next decade. Machine learning, though, has the greatest potential for growth, and that's an area we're beginning to focus on. Some of that growth in machine learning will come from more performant and more efficient hardware architectures. The ML architecture in PS5 Pro is quite good, but we did not, in fact, achieve that holy grail of a fully fused network when running PSSR. It's close, but PSSR can't quite keep all of its intermediate data on chip, and therefore does, to some degree, bottleneck on system memory access. We see definite room for improvement in future ML hardware. An additional source of future growth will come from more sophisticated neural networks. When fewer higher quality pixels are combined with the right neural network, the result is richer graphics. One way to look at this is supportable upscaling ratio. If we're able to create quality imagery with a 2:1 upscale, and can then improve the neural network and reach the same image quality with a 3:1 upscale, then the effective power of the GPU has roughly doubled. And that stacks on top of whatever is being done to speed up rasterized rendering or ray tracing. There's enormous potential here. We also hope to be heading towards multiple uses of these CNNs within a frame, not just super resolution, but also some of the other targets I was talking about, such as the denoising that's needed when doing optimized ray tracing. Through PS5 Pro, we've developed some good understanding of hardware design for machine learning, as well as neural network design, and we intend to continue this work with a pinpoint focus on games. Of course, as part of their broader strategy, AMD is pursuing many of the same goals. And so I have some very exciting news to share. We have begun a deeper collaboration with AMD. For the project name, we're taking a hint from AMD's Red and PlayStation's Blue. The code name is Amethyst. With Amethyst, we've started on another long journey and are combining our expertise with two goals in mind. The first goal is a more ideal architecture for machine learning, something capable of generalized processing of neural networks, but particularly good at the lightweight CNNs needed for game graphics, and something focused around achieving that holy grail of fully fused networks. In going after this, we're combining the lessons AMD has learned from its multi-generation RDNA roadmap, and SIE has learned from the custom work in PS5 Pro. But ML use in games shouldn't and can't be restricted to graphics libraries. We're also working towards a democratization of machine learning, something accessible that allows direct work in AI and ML by game developers, both for graphics and for gameplay. Amethyst is not about proprietary technology for PlayStation. In fact, it's the exact opposite. Through this technology collaboration, we're looking to support broad work in machine learning across a variety of devices. The other goal is to develop, in parallel, a set of high-quality CNNs for game graphics. Both SIE and AMD will independently have the ability to draw from this collection of network architectures and training strategies. And these components should be key in increasing the richness of game graphics, as well as enabling more extensive use of ray tracing and path tracing. We're looking forward to keeping you posted throughout what we anticipate to be a multi-year collaboration. Let me get back to PS5 Pro for one final moment. You've now heard a bit about our fairly intense last few years building this console and developing PSSR. There's been so much learning for us as we delve into these new technologies. But the payoff, as I said in my PS5 tech video a few years back, is in the games. And by now we know to expect the unexpected. It's an absolute guarantee that the development community will grab a hold of this technology and move in a direction that we never could have anticipated. Personally, I can't wait to see what they do with it. Thank you for your time today.
PlayStation